So limit state of collapse, that is flexure, or you can say when member is subjected to bending, we can refer the guidelines mentioned in IS 456 in clause number 38. So the design of limit state of collapse in flexure, which we are going to discuss today. So what are the various assumptions which we have to keep in mind, or so that we can apply or we can use the limit state design methodology? That is first type of a limit state of collapse. Now here very first assumption, which is generally we take in strength of material also, that is when you develop the theory of simple bending. So same assumption we are going to take here, that plane sections, very first assumption is plane sections normal to the beam axis. So definitely there will be one beam which we are going to take into consideration, which will be subjected to loading, and corresponding due to the load some movements will get developed, and the after effect of that movements will be there will be some bending in the beam. So if you are taking into consideration a beam and you want to do the analysis of that beam, then what is the first assumption? That plane sections which are normal to the beam axis before the loading, before the bending, will also remain plane after bending. So why we are taken this particular assumption? Because we want to use this aspect of the theory, that is strains will remain proportional to the distance from the neutral axis. If we are using or taking into consideration this particular assumption, then this theory we can easily apply, that strain are proportional to the distance from the neutral axis. Now see here in this figure, figure A, and this figure is corresponding or to assumption A basically. Now in the top you can see there is a beam, any type of beam, any type of supports it may have. Now before bending, let us assume that beam is a state member, and here red color we are taking, let us take two sections. So this section, basically this section is perpendicular or normal to the axis of the beam. This black color line is showing the axis of the beam, and this red color is showing the section. We have taken two sections into consideration. So these two sections initially they are plane, and you can see here after the loading on the beam will be subjected to some movement, as I have already told. So these type of you can say there will be some movements will be acting on the beam, and due to those movements there will be some bending in the beam. So you may see here that in the top fiber of the beam is under compression and bottom fiber is under tension, as we have already studied in the bending theory. Now you can see here before bending as well after bending, these plane these section, these planes which were normal to the axis of the beam, and before bending they were just like a plane surface, so they will remain plane. That means there will not be any bending in the section which is perpendicular to the axis of the beam. So that's why we are taking this first assumption, so that we can utilize this theory that strains are proportional to the distance from the neutral axis. Now second very important assumption which we have to take into consideration, the maximum strain in concrete. Now when there is a concrete member and it is subjected to loading, there will be some strain will automatically develop. So what will be the maximum strain? So that we have to restrict here, that is epsilon Cu. Cu is for concrete we are taking into consideration, and epsilon is symbol we generally use in case of strain. So maximum strain in concrete at the outermost compression fiber. So if we are considering this beam, then this fiber will be the outermost fiber, and this fiber will be the lowermost fiber. So outermost compression fiber is taken as 0.0035 in case of bending, because we are talking about the flexure effect, that is bending effect. So in that bending, it is our assumption that maximum strain in concrete which is allowed in bending, that is 0.0035. No doubt maximum strain will be at the topmost or bottommost fiber, and the topmost fiber there will be compression, bottommost fiber there will be tension. So we are taking into consideration compression behavior. Now in this figure B, there is we have shown a rectangular section of a beam, and at the bottom we have provided some reinforcement. So this is the sectional view of that beam. That means this beam is having some longitudinal dimension. Now you can see here at the centers, almost at the center, there is a dotted line, and this dotted line is known as neutral axis, NA. So what is neutral axis? You already know that neutral axis is the axis within the section of the beam where, or level of the beam where there is not any compressive stress, or there will not be any tensile stress. As well as we can say that the fiber which is at neutral axis level, it will not be subjected to any strain. It is our assumption or for the development of the theory. Now you can see here at the bottom level, at the level of steel, strain is given as epsilon st. And to apply this theory, what is our basic assumption? This is our assumption. That means strain in the topmost or outermost compression fiber, this value of strain, if you can write here that it is 0.0035. So this is the second assumption, that maximum strain allowed in this theory in the compression fiber, topmost compression fiber, that is 0.0035. Now you can see here the strain variation is linear variation, and it, as you move from the neutral axis to the any other fiber, to the topmost fiber, then you can see here the graph is a straight line. So that means it is a linear variation. And how it is because of our first assumption that plane section normal to the beam axis remain plane after bending. So if this first assumption is not taken into account, then you can't use this strain graph for the section of RCC section. So to take this application of this graph, and to make our calculation easy, we are using or taking first assumption, as well as then accordingly we can take the second assumption. So second assumption is possible when only first assumption is valid. Now very third assumption is the relationship between the compressive stress distribution in concrete. So you are aware that in RCC we are assuming that concrete will be taking care of all the compressive stresses and steel will be taking care of all the tensile stresses. So what is the third assumption? The relationship between compressive stress distribution in concrete and the strain in concrete may be assumed to be a rectangular type of relation, trapezoid or parabola, or any other shape which result in the prediction of strength in substantial agreement with the results of the test. So all these assumptions we have taken from IS 456. So in the next slide you will be able to understand what is the exact meaning of this third assumption. Now fourth assumption is an acceptable stress strain curve, which we are showing here. So I have taken figure number 21 because in IS 456 there is figure number 21 which we are going to utilize here also. So this is the figure number 21. So I have taken here also figure number 21. So no need to search out figure number 20 or 19. That will not be here. So what is figure number 21? It is the stress strain curve. That means the relation between stress strain for concrete, which is applicable in case of a limit state theory. So for design purpose, now you can see here three type of graphs are shown, and this first graph, second graph, third graph we will able to understand now. For design purpose, the compressive strength of concrete in the structure shall be assumed to be 0.67 times the characteristic strength. You may remember during the preliminary lectures on concrete technology, we have used this parameter 0.67 earlier. So if you find any difficulty, you can just go through the previous lectures also. So, and the partial safety factor gamma C, we will be taking 1.5. That will be applied in addition to this. So that means now you will be able to understand here. See here, very first curve, that is giving you the graph for characteristic compressive strength of concrete. So this graph is basically the result of the testing of the concrete cubes, and that means when you are testing the concrete cubes in the laboratory, you may be getting this type of graph between stress and strain. Now second graph, this is basically when you will start using concrete in the structure. So its behavior, or you can say the strength of the concrete cube, will differ from strength of concrete when it is actually in the structure. So that's why we have taken 67% of characteristic compressive strength due to using various type of a size factor, etc. So that's why this second curve is giving you the concrete in structure, and the first curve is giving you concrete in cube. That means when cube are tested, and this is the application of that concrete. So we are taking only 67% of a characteristic compressive strength. Now third graph will be for design purpose. So it will be that giving you the design strength. Now how you will get the design strength? That means you are taking 67% of the corrective strength, and then you are applying partial safety factor for material, that is partial safety factor gamma C for concrete 1.5. So what you are doing, you are here doing the compressive strength which you have taken of concrete in structure, which is going to be utilized in the structure. You are dividing it by partial safety factor. Gamma M is for material. So here we have replaced it as a gamma C. C belongs to concrete. So that means what you are doing, you have to divide 0.67 FCK by gamma M. So ultimately, when you divide 0.67 by 1.5, you will get this factor 0.446 FCK. So now you can easily analyze what is the actual strength of concrete, that is FCK, and we have reduced it up to 44.6% for the design purpose. So that's why here we have taken into consideration all possible parameters. That means size of the member, because strength of cube in cube is a very small size of the cube material of concrete, which can be controlled, but later on you are getting to utilize it in structure. So we are taking in the, as per the limit state methodology, only 44.6% of characteristic compressive strength of concrete. Now you can think here, if you are taking M20 grade of concrete into consideration, then FCK will be 20 MPa, but during the design calculation you are taking 44.6% of that 20 MPa. That will be the design strength of the concrete which you are going to utilize. Next assumption is the tensile strength of concrete may be neglected. So that's already we have discussed that when you are using concrete in RCC structure, you are ignoring the tensile strength. Whatever be in the concrete having tensile strength, you are ignoring it, you are neglecting it. And similarly, you are neglecting the compressive strength taking capacity of steel also. So for concrete we are ignoring the tensile strength, and for steel we are ignoring the compressive strength. Now another very important you can say the assumption which we have to take into consideration, the stresses in the reinforcement are derived from the representative stress strain curve for the type of steel used. So whatever be the type of steel you are going to use, whether it is mild steel or whether it is high strength steel, so accordingly you have to take the help of the stress strain curve of that particular type of steel. And for design purpose what we are doing, we are using a partial material safety factor gamma S for steel, which is 1.15. So we will be able to understand it in the next slide. Now in continuation to the previous slide, we will be taking into consideration these typical curve for steel which are given by IS 456 in figure number 23A and 23B. So this is figure number 23A where cold work deform bars are to be used. So this is the stress strain graph for that particular type of steel. So accordingly this will be the graph, actual graph of the stress strain graph, actual that type of steel, and Fy is the yield strength. You can understand here that 0.002 is the strain which we have taken as a proof strain, a proof stress according to 2% of the. So accordingly beyond this you will be considering that graph is just like a straight line. So this is the yield strength of the steel. And for design purpose what we are doing, we are dividing this yield strength by partial safety factor for material for steel, that is 1.15. And similarly, and this is the another graph which is recommended by IS 456. If you know the definite yield point, that means you are aware that what is the actual yield point. Yeah, so in this graph will be just like this is straight line curve, and later on it will curve. So Fy is the again yield strength of that particular steel, and we will be dividing it by 1.15. So this lower curve which we are getting after dividing it by partial safety factor for steel. So this is the actual design curve which will be applicable in limit state methodology when you are going to do the calculation for designing or analysis of the structure. So first of all you will be doing the analysis, and later on according to that analysis you will be able to design the structure. That means you can work out the dimensions of the structure. Whatever we suppose there is a beam, then what will be the cross section dimension, that you will be able to work out as well as a material. So when you divide Fy by 1.15, so what will be the strength of steel which we will be taking? That will be 87% or 0.87 Fy. So this is the strength of the steel which we will be taking into consideration, that is the tensile strength of the steel which we will be taking into consideration while doing the calculation. So that means we are taking 87% of the yield strength. Now another important assumption, that is the maximum strain in the tension reinforcement in the section at failure shall not be less than. Now we will be using, now if you see this graph this graph number 23A, here strain which we have taken, that is 0.002. So corresponding to that strain we are getting the value of yield strength. So it is very much clear that this, when you are taking the value of yield strength of steel Fy, so that will be corresponding to the strain 0.002. Now what code is saying, the maximum strain which is allowed, maximum strain in the tension reinforcement shall not be less than. Now Fy by 1.15 we have taken here, that is 0.87 Fy, Now stress divided by modulus of elasticity, it will give you strain, and plus this 0.002 which we have taken here. So this much will be the maximum strain. So Fy, you know, characteristics, strength of steel, and Es is the